Okay, so we would like to show this very simple statement, which is the basis behind the Eratosthenes sieve. So it says that if we have a composite number, then it has a prime divisor that does not exceed the square root of that number. Let's see the proof of this. It's very, very simple. So let n be composite. So the moment we say that it's composite, we mean that it has to be greater than 1. In fact, the smallest composite number is the number 4. Then there exists A, comma B in n. Here, of course, we want this number to be natural. There exists A, comma B in n with both A and B less than n and greater than 1, such that n is equal to A times B. Okay, that's what it means precisely for a number to be composite. Okay, assume that A is less than or equal to B. I mean, you have two numbers, one of them has to be less than or equal to the other. And without loss of generality, assumes that A does that. Then A squared is less than or equal to, or think of A squared as A times A. And this is less than or equal to A times B, which is equal to n. So if you consider that A squared is less than or equal to n, that implies that A is less than or equal to square root of n. So we take the square roots of both sides. So if P is a prime divisor of A, then any number greater than 1 has a prime divisor. Any natural number greater than 1 has a prime divisor, prime or composite, whether that number is prime or composite. Then P is also a divisor of n, right? If a natural number divides a second natural number and the second natural number divides a third natural number, then the first natural number divides the third one. So in that sense, divisibility is transitive. And P is less than or equal to A, and A is less than or equal to square root of n. So in other words, P is less than or equal to square root of n, which is exactly what we wanted. We just have here one extreme case where n is the square of a prime number. Only in this case, we will have equality. In all other cases, we can find a prime number which is strictly less than the square root. Not that this matters, but it's a good idea to understand when equality occurs here. And that's it. That's how this very simple proposition is proven. Thanks for watching.